All right. So we have 25 students now and we're live on YouTube. So I'm super happy to introduce Thierry Giamarchi, who's going to be our second speaker of the day. So I really became aware of Thierry's work attending the BEC conferences in Saint Philou. And I'd like to wonder, actually, Thierry, you're going to be able to go to the conference this year?
I hope to be able to go this year to the conference live, so we'll see.
Yeah, so fantastic. Yes. I hope to be able to make it to a different country, which is dubious. So anyway, Thierry's made a real art form of understanding both numerically and analytic 1D systems, both in terms of static and dynamical properties, just in a whole bunch of amazing ways. And I'm sure that we're going to be seeing some of that today. And as Leo was referring to, not only is Thierry a wizard of science, he's also literally a wizard. And unfortunately, we're not going to get to see the actual wizardry of stuff, but we'll get to see the scientific goodness. So thank you very much for joining us, and I hope everyone enjoys your lectures.
So thank you, Jan, for the introduction. And before I start, I wanted to thank all the organizers of the conference, and also, of course, Leo, for the invitation to participate to this school. It's always a great pleasure to be there, even if it's by Zoom. You cannot see it, but I'm wearing the Boulder School T-shirt of 2013, which was a great experience. And I really deeply regret not to be able to be there in person for this session. So welcome to all. My task in this school is to tell you a little bit about one-dimensional quantum systems, and you already heard several talks that mention 1D quantum system, like Antoine Brois, for example, to some extent also Nigel Cooper. So I'll try to assume that you don't know much from the theory of these systems, but don't hesitate to intervene, don't hesitate to tell me to speed up, or on the contrary, to slow down. Again, the idea is to as Emmanuel was saying in the previous lecture, it doesn't matter, we are not running a marathon. We'll cover what we cover, and what is counting is the input flow and not the output flow. So don't hesitate to regulate the flow of what I'm saying. If you feel you have already good knowledge of what I'm saying, don't hesitate to tell me to speed up. If not, don't hesitate to ask questions, interrupt me, and keep me on my toes. If you don't do anything, I usually tend to speed up, so don't hesitate to ask questions. Okay, so I'll try to alternate between the iPad and the slides. I would have loved to give a lecture on the iPad or on the board, but given the format of the conference, it will be a little bit complicated. So I'll start with the slides, and then we'll move, when we go to the theory part, more to a traditional way of writing Okay, so what is the idea of what I'm going to tell you? Well, you already heard both in the talks today of Emmanuel, in previous talks, that there are wonderful effects that happen in quantum systems when you combine the interactions and quantum effects, and I'm going to try to put a little bit of formalism around this. So we have 3 lectures together, so I'm going you the menu of the lectures. Today we'll do things that work. I will cover basic notions of the theory of one-dimensional quantum systems. I'm sure some of you have heard some of the names, like Tomonaga-Luttinger liquids and so on. These are theories that by all means are relatively well established, work pretty well. And so today I would say we are doing physics which is well understood and which has been extensively tested. We'll mostly discuss equilibrium things. Tomorrow and in the last lecture, we'll move to things which are much more open, with much more open questions. And I had to make choice because of course it's impossible to cover everything which is is remotely connected to 1D. It might be 1D, but it's a pretty vast world. And so I've chosen to try to make contact with other lectures you got to discuss in the second lecture mostly notion of transport. So what happens when you try to set a system out of equilibrium, but maybe a little bit less violently than Emmanuel did, but by connecting a system to reservoirs, for example, and trying to pass a current, or giving the system a small kick, something that Jan knows very well. What is the effect of interactions? What is the quantum effects? What are the consequences for transport of charge or spin in these systems? This will also be an excellent occasion to revisit a little bit the disorder effects, maybe in a perspective which is a little bit different than the one you already heard so far, because you focused mostly on the many-body localization effects, high energy physics, very far from equilibrium. Here we'll wonder what the disorder is doing close to the ground state, not too far from equilibrium, and we'll explore a little bit related questions, spin transport, energy transport, and so on. So this will be mostly the second lecture. And then the third lecture, we are going to boldly where no theorist has gone before, which is to try to go between 1D and 2D or 3D. As I will try to convince you today, we have pretty good methods to tackle 1D systems, as long as it's equilibrium, blah, 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 blah. But of course, we lose mostly our control of these methods when we move to higher dimension. And there, for example, if you remember the lectures of Feshbach, you know that there are really outstanding problems that we need to solve. And one way to attack these problems is to try to study what people call the dimensional crossover. So namely, what happens when you take many 1D structure and you try to couple them together to reconstruct a higher dimensional system. So we'll examine these issues. There are structures which are called ladders that we'll discuss a little bit, which will be also a good occasion to discuss in connection with transport the Hall effect, because the Hall effect is particularly nice to study in cold atomic systems. And with that, I think you will already have a flavor of a certain category of problems that pertain to one-dimensional system. Of course, it will not be the end of the story, but I would say it's what we should be able to do in 3 lectures. Okay, so before we start the lectures per se, I wanted to justify to you a little bit why one dimension. Why is it fun to look at quantum effects and interaction effects in 1 dimension? And I could give you some what I would call noble excuses concerning technology, creation of materials which are interesting for future applications and so on. I will skip this. I will try to stay, at least for this lecture today, very focused on the cold atomic gases. I will not refer too much to condensed matter, not by lack of motivation, but by lack of time. And so I will give you purely theoretical motivations, why to look in 1D. And I will try to destroy as much as I can 3 urban legends that exist on 1D systems. And I'm sure you have these urban legends in your head. And the first urban legend is that 1D is a toy model. You study 1D because you want to understand higher dimensional systems, and it's complicated. So you start first by having single, integrals rather than triple integrals and whatever. And that's the first urban legend. The second urban legend that I want to shoot down is that 1D systems are only for theorists. They don't exist in nature. They are a construction of our mind, of our spirit. I don't need to shoot down this one very hard because all the speakers before me already shot it down, starting with probably Antoine, and just this morning for you, afternoon for me, Emmanuel showed beautiful system in 1D, so you know that 1D is not just for theorists. And the last urban legend, which is the most dangerous of one, because today I will actually go with this legend is that everything is understood in 1D. You know, if you deal with 1D, you know, at the end, it's kind of an engineering problem. You know everything. There is no research to do there. And I will, of course, try to convince you very seriously in lecture 2 and 3 that this is really not the case. But today, we'll go with this urban legend, the urban legend number 3, and we'll indeed see things which are working. So let's forget about this. Now, what is it in 1D that makes the combined study of quantum effects and interactions especially interesting? Well, that you know very well, and some of you are probably familiar and you already heard the words Fermi liquids, for example, which is a great theory due to Lev Landau in higher dimensional fermionic system, which says that even if the interactions are strong, in a way, you get excitations in your system which look like free particles, which people call Landau quasi-particles. And that you understand very well. Imagine you're in a room and you have between the particles even hardcore interaction. You cannot put two particles at the same place at the same time, which is what basically even us have as a typical interaction. And you know very well that we can behave as individuals. We just zoom between the other particles, and in a way we are not affected at all by the interaction. So in a way, in more than one dimension, even if you have extremely strong interactions, well, at the end of the day, it's relatively easy to keep your individuality and still behave as a free particle. Well, if you are in 1D, this is strictly impossible. Imagine that you have a situation like this. If you queued for something from the time before going to a movie theater or to a cafeteria, you know very well that if you have a line like this, then if this particle tries to move and interact with this one, it pushes it, which pushes the other one, which pushes the other one, and so on. So individual motions become impossible, and only collective motion are possible. So in 1D, even a weak interaction, forget strong interaction, even a weak interaction will have dramatic effects by transforming any individual motion into a collective one. So in 1D, it's impossible to escape the consequences of interactions, even for weak interactions. If you want another image, think about cars on a highway. Again, a car cannot behave as an individual particle if it's confined to a single lane. If you want to recover your individuality, it means you're able to pass the other cars, which means you need more than one lane. Here we would have a 3-lane system, which is also called in more scientific term a 3-leg ladder. This will be for lecture 3. And in that case, you do recover some level of free particle. A car can zoom between the others. But if you are in 1D, only collective excitation can exist. So it immediately tells you that there will be very drastic consequences of interactions. From the theoretical point of view, there is a second consequence which exists in 1D, which we have to deal with. Most of our understanding of correlated materials is resting on mean field approximations. You know, it has various names. It's called RPA. It's called Bogolyubov approximation. It's called, you name it. Usually what you assume is that, for example, for bosons, you have an object which has an amplitude and a phase. And if you have Bose-Einstein condensation, you would say, okay, the phase is frozen, and then I do small expansions around an equilibrium phase or around an equilibrium amplitude. And we do perturbation, we get back to a quadratic Hamiltonian, and then we can solve. Well, in 1D, you can show there are, quote, theorems which tell you that this is the case, that essentially because of these very strong fluctuations that exist, it's essentially impossible to break a continuous symmetry, which means that you can forget about most of your mean field approximation. They go directly to the trash can. So most of the methods and the approximation that we are used to and which work very well in higher dimension become inefficient in 1D. And we need to completely reinvent the theoretical arsenal to be able to tackle this problem. So this is something that makes it also extremely interesting from the scientific, the theory point of view, because we also need to understand what happens in a system which has by nature very strong desire to fluctuate and which is unable to order, or which will have very strong reluctance to order. So all this makes 1D an exciting place to find new effects, new physical effects, and also new theoretical tools. I won't discuss, as I mentioned, condensed matter examples in great detail. I will show, of course, a couple of them, but I just want to point out that even before the advent of cold atoms, condensed matter is a place where you can find many one-dimensional systems. Here is organic conductors, superconductors even, nanotubes, so-called magnetic ladders, which are compounds in which you have copper side carrying spin 1/2 here on the blue sides, and which have this ladder structure on which we will come back. There are quantum wires, which are semiconducting structures, which are thin enough that they can be assimilated to 1D systems, and more recently, edge states in topological insulators or quantum Hall or quantum spin Hall effect. So all these are good realizations of 1D systems. As I said here, I will more insist on the ones that can be realized in the cold atomic gases, but it's good to keep in mind that, of course, one has these two fields, condensed matter and cold atomic gases, that go hand in hand and which provide complementary things. One of the reasons to also give you a lecture on 1D is actually that for reasons which are sort of serendipitous, there was an actual drastic evolution of the 1D world in the last 20 years or so. This is an old field. This is a field which goes back to the 50s and the 60s. But one could imagine that it reached a culmination point in 80s with the work of Duncan Haldane, on which I will come back. But actually, in the last 20 years, there was a complete revolution in the 1D world. New methods arrived. Fantastic numerical methods, density matrix renormalization group, which was extended to time-dependent correlation, to out-of-equilibrium situations. People from the exactly solvable model, better ansatz, managed to compute correlations, which is something they never managed to do before, and so on and so forth. So there was really a technological progress on the theory side. There were a host of new systems, in particular thanks to the advent of cold atomic gases, but not only. There were fantastic systems that were realized with magnetic insulators, and this completely changed the experimental situation. And last but not least, people simply ask new questions that nobody asked before, even if the field was around for a very long time. What happens if you have very strong spin-orbit coupling, for example? What happens if you put this 1D system out of equilibrium, and so on and so forth? So all this evolution makes it fun to either use old tools to investigate new problems or to forge the new tools that you need to either fight with new experimental systems or to address these new questions. Voilà, that's all what I wanted to tell as an introduction. Let me finish with two things. Before we go for the real part of the course, I would say, again, this is more like a colloquium way of sending the message rather than a course, how to treat. So of course, during the lectures, I won't go too much into the practical technical details, but I want to give you a kind of take-home message. And also that's a good moment to do a history page, if I can say, and show you the hero of the field, because I think they fully deserve it. This is a field that started with standard many-body theory. And there the hero are Tomonaga, Luttinger, and then there were very strong works of the Russian school, Lev Gorkov, Igor Dialoginsky, Anatoly Larkin. These guys used good old-fashioned diagrammatic theory to hammer down the first results on 1D systems. And believe me, that's really not the good method to obtain the results. But nevertheless, they managed to obtain the first results and to obtain them right. And they really founded the field. We'll see much less painful methods, but these are the people who really in the 60s founded the field. Then, because in 1D, we have the fantastic chance to have exact solutions, these are methods that were, of course, extensively used. Here are two heroes, Hans Bethe himself and Elliott Lieb. You have probably heard in previous courses of the Lieb-Lininger model, which is bosons plus contact interactions. This model is solvable by the Bethe-Ansatz technique. You have to realize, however, that very often on a model which is exactly solvable, the only thing you know is that it's exactly solvable, but you don't know anything about the solution because it's hard. Then the next level is that you know the solution for a finite number of sites. Then you know the thermodynamics, and 60 years after Hans Bethe original paper, for two models, the Lieb-Lininger model and the XX spin chain, people could use Bethe-Ansatz to compute correlation functions. But very often, having an exactly solvable model is really not, I mean, you have to fight hard to really extract physics from this knowledge. But nevertheless, several results were actually obtained first, like the presence of a gap in the Hubbard model at half filling was first obtained by Bethe-Ansatz, believe it or not, and not by field theory, which I find a remarkable thing. Then you have field theories. And that's the thing I'll try to show you during this first lecture. The field theory have the drawback of not being exact. They are asymptotic method. They give you access to the physics of the problem at large distance, long time, and low energy, which means probably you should not push the problem too much out of equilibrium, because otherwise you excite a lot of energy states at high energy. But if you're interested in low energy physics, long time, large distance, this is a fantastic technique. And one of the methods which is known as bosonization, and there is conformal field theory, which I will try to introduce to you, is particularly efficient to reveal the nature of the physics in 1D. And there, of course, there are various heroes, but the three main are Alan Luther, the late Vic Emery, and closer to us, Duncan Haldane, who wrote absolutely seminal paper and invented the concept of Tomonaga-Luttinger liquid, which I will explain a little bit later. And last but not least, quite remarkably, you have remarkable numerical techniques in one dimension, and the most efficient, so Monte Carlo and so on, but the most efficient of all these techniques is the density matrix renormalization group, which was actually invented by Steve White in the early 90s, and then was completely reinvented in the mid-2005 by various people, in particular by the two groups of Steve White and Uli Schölvöck. There are many other people who were associated with this rediscovery, Corinna Collat, Andrew Daly, Jeffrey Vidal, and so on and so forth. And these numerical techniques provide an essentially exact way to tackle not only static correlations, but dynamical correlations, and even time-dependent Hamiltonians. And you see immediately that this is complementary of the field theory. Numerics is efficient at short distance and short time, Field theory is efficient at large distance and large time. And one of the things which is a take-home message in 1D is one of the remarkable things that we learned how to do in the last 20 years is to make these three apparently uncorrelated techniques work together and extract the best of each technique and feed it in another technique in a way that I will explain. So use numerics to feed field theory or use exact solution to field theory to get the best of both worlds and obtain through this cycle of theory an essentially exact description of the problem. Unfortunately, the same program cannot be done yet in higher dimension. And that's one of the reasons why we have much less knowledge in higher dimension of the physics of correlated problems than what we have in one dimension. But I will show you how we can combine this to really extract what I would call essentially exact solution, even for models which are not exactly solvable. Okay, so that's of course the spirit of it. Now, if you want references, I've put this on the slides. You will have much more in these various references than you ever want to know in 1D systems. But if you want to look at the detailed techniques, of course, that's one of the places where you can go on. Some of the references, like the book in 1D, are of course very detailed on the techniques. The review of modern physics that I've quoted here is more oriented towards bosons. And the last two references contain experimental example in condensed matter that I will not discuss too much in detail. Okay, and now let's start really in earnest and discuss the 1D physics. But before, let me pause for 1 second and ask if there are questions. Good. I didn't say much for the moment. I just blatted on the generalities, but okay, no questions. Okay, so let's start first with the first thing we need to answer, which is what is a 1D system? So I hope you see the iPad correctly and that it's readable. If not, don't hesitate to shout and protest. Okay, so let me ask you the question. What is for you a 1D system? Because, okay, forgetting a little bit about string theorists, we live in a 3D world. So everything real around us is 3D. So how can I talk about 1D systems? Anybody want to risk it? No, you're very quiet. I guess it's the 4th week of Zoom. I would also have the brain leaking through the ear or something like this. That's
Well, it's a system that has strong enough interaction on along one direction, and then it's basically decoupled in other directions. Although we do talk about 1 plus 1D sometimes, right? Like, because sometimes it can be
so the plus 1 is the time. So this
okay,
is just to say it's a quantum problem. So we say plus 1 to remember that there is the time. But actually, 1D is not necessarily linked to the presence of interactions in one direction. I could also discuss, for example, free fermions and wonder whether they are 1D systems.
If they're confined, I guess.
Yes, so that's the first direction. So let's explore this. So the first yep.
Let me just interject. It was pointed out to me that for some reason, the iPad resolution looks a little bit low. So I don't know if there's an easy fix, but write big, I think, is the easiest fix.
Okay, that's the easiest fix that I will do. Thank you. So first, is it okay?
Yeah, at that size, it's very readable.
Okay, so confinement, indeed. Let's examine a system which would be in a box, and I'll do it in two directions just for simplicity. So I would have something I will call Ly. I will have something I will call Lx here, and I will quantize. And because I don't want to bother about box quantization, let me just take periodic boundary conditions quantization. It doesn't really matter at that stage. So I will say that Kx is 2 pi over Lx times an integer nx. Ky is 2 pi over Ly times an integer ny. And so if I look at the energy of a particle, it would be Kx squared over 2m. I do h bar equal 1, huh? As any respectable theorist. No, I'm lazy, that's all. Plus ky square. And of course, then it means that I will have this 2 pi square over Lx square 1 over 2m times nx square plus 2 pi square over Ly square times 1 over 2m ny square. So let me assume that Lx is much, much larger than Ly. Now, if Ly is very small, it means that every time I will change ny, I will get a huge shift in energy. If I take ny equals 0, this term is 0, but then when ny is equal to 1, this term will contribute. So let me, on the contrary, if Lx is large, I have many, many, many quantum numbers here, and this is roughly speaking a continuous variable. So let me draw here the energy written in a slightly different way. So I will write the total energy as a function of the quantum number Kx, which again is strictly speaking is 2 pi over Lx times nx. And I will use ny as another quantum number. So I will have a first curve here, which is with ny equals 0. Then I will have another curve with ny equal 1, and so on and so forth. Ny equal 2 and whatever. And now, if I have, for example, fermions, I will start to feel this system by occupying states up to the Fermi level. No interactions for the moment. And I will be here. So all these states are occupied. All the other states are empty. Okay. Now, let's imagine that I'm looking at the excitations of the system. If I look at the excitations of the system, I can take particles here, excite them here, scatter them, do a lot of things. And I will do it in a bandwidth here, which is of the order of the temperature, the strength of the interactions, something like this. Otherwise, I don't have the energy. Now, you see that if these two bands here are separated enough, I will never be able to change the quantum number which is associated to ny. So this is not like in my drawing, they are too close to each other, but let's imagine I separate the red band by much more. So it means that in any scattering process, thermal process, ny is constant. So the only quantum number that can change is the quantum number which is associated with the longitudinal direction. Well, that's a 1D system. So 1D system only exists because of quantum mechanics, because of the quantization of the transverse degree of freedom. If you didn't have quantum mechanics, then of course you could never make a channel which is narrow enough in a way so that you would get 1D system unless you take particles which have a finite extension. So 1D system here is something for which the wave function, if you want psi of x and y, is a wave function psi of x that will change depending on scattering and whatever. And the wave function along y is fixed, let's say, with a fixed quantum number, ny equals 0. So that's one way to realize 1D system. Confined enough in the transverse directions, then the transverse wave function is fixed once and for all, and then all the quantum mechanics property only depend on one quantum number. So that's one way of getting 1D systems. Let me give you a second one, which is incoherence. And this is a little bit more subtle, so I will just mention it, and we'll come back to it in the third lecture. Let's imagine that you have a system, and I'll do it in 2D for simplicity, which is made of many tubes which are connected by a tunneling term Ty. The energy of the system is the energy along X minus 2Ty cosine Ky, which would be the tight binding energy of particles hopping from, so particle can move here, but they can also hop from one chain to the next. And therefore, in a tight binding representation, this gives a correction to the energy, which is this one. So if I was, for example, looking at the curves of iso energy, so let me try to write it that way, do it like this. So this is, for example, Ky. And let's say I look at curves so that this energy is equal to EF, let's say some Fermi energy. If Ty was 0, this would just be here 2 straight lines. This corresponds to the intersection of the curve Ex of K, for example, of Kx with the Fermi energy. So for example, I would have here an intersection, and this would define this 2 straight line. It's completely independent of Ky. Now, if I put this distortion here, this energy, then I'm distorting the surface of constant energy in this way. I'm doing something like this by adding the other dispersion. And this is, of course, of the order of 4 Ty. And of course, the fact that this is not flat reflects the fact that particles have a coherent hopping between the various chains. Now imagine that the temperature is much larger than 4 Ty. The temperature will blur completely this surface. And then you're unable to say whether the surface would have been flat or is distorted by the tunneling. And therefore, you're not able to say that the system is 2-dimensional. So actually, another way of saying it is that you cannot jump coherently from one chain to the next if T is much larger than Ty. In other words, you try to jump, but before you're scattered by a thermal excitation, and therefore the various chains are a kind of independent collection of chains. But you cannot build a coherent wave function that goes across the chain. So you're 1D again. And that's something which is very interesting because it gives you actually a control. You see that essentially, if I look as a function of the temperature, I would have here a certain crossover temperature above which my system would be 1D. So this is, let's say, of the order of Ty. And let me put a question mark because actually I lied to you. That's not correct. interactions will modify the scale. But essentially, my system is 1D at high temperature, but will become 2D or 3D at low temperature. But nevertheless, at high enough temperature, there is a good regime in which you can consider that the system is one-dimensional. Okay, so now we know what is a 1D system. And so let's look a little bit.
Short question.
Yes, of course.
How does this T star or Tx compare with the Fermi temperature? Don't you have run into trouble? You want to be degenerate. On the other hand, you need to be
so you're totally correct. So here, my sort of implicit assumption was that Tx is the largest energy scale in the system. So my Fermi energy is much larger than Ty. So this T star here is assumed to be much smaller than the Fermi energy of the system. You see the Fermi energy is fixed here. So this is of the order of, let's say, whatever, 4Tx if you want. And the Fermi energy will be of this order. And now let's say I put a very small tunneling between the chains, which is a situation that can be realized easily in the cold atomic gases. And then I can have this. So if you want, here is my Fermi energy, EF. So my system is quantum degenerate because my temperature is smaller than the Fermi energy and is quantum degenerate 1D. Then when I lower further the temperature, it becomes quantum degenerate 2D or 3D. Of course, if I have both Tx and Ty, which are of the same order, then it's a slightly different situation because then I collapse the 1D regime and I just go from a system which is 2D or 3D quantum at low temperature to a system which is fully incoherent at high temperature. But if I have enough difference between the Tx and Ty energy scale, I can open a window in which I will kill the coherence only along one or two directions in space.
Okay, just to verify, within the tube, you're not 1D. The tube itself is a three-dimensional tube, but it's the fact that you have this incoherence that kind of restores the one dimension.
So the tubes are whatever they are. I don't care. Again, because the tunneling is, let's say, small, means that, for example, we're still with a situation where we would have, for example, an optical lattice, and each one of these tubes would actually correspond, as Emmanuel was showing, to a wave function which corresponds to the ground state of the harmonic oscillator at the bottom of the optical lattice. And then I have all the quantum numbers along X that corresponds to the wave function that I was discussing before. So if you want, each tube is indeed 1D in the quantum sense that I defined before. So here I just have a box. Nothing can leave my system. I'm saying that even if there is little tunneling to a next tube, as long as this little tunneling is smaller than the temperature, my system remains 1D. Of course, if each one of these tubes has many, many levels that are accessible already, then I'm not in a situation where I would have a single dispersion here, but many, many bands, and then I'm not 1D. You can always classify this. For example, if you had two bands, you could also say it's like having two chains. So this will be what we call the ladder a little bit later, but then it's a more complicated problem. So yes, for this second part, I need each one of the tubes to be in the 1D regime. Is it clear? Are there other questions on that one? Are there other questions on that point? Because it's an important point that we will need to understand. It also tells you, you see, that if you crank up too much the interactions, you have to worry about the presence of these other bands. Because if U is gigantic, you could excite something from here and put it in one of the higher excited states here. And then you have to make sure that your system stays 1D by pushing up these bands to higher level. And that's an experimental difficulty.
So Thierry, you probably said this and I missed it, but you're talking about interactions that are at least local within the tubes, not
interactions for me, unless specified for the moment, will always be contact interactions, which I think covers 99% of the cold atomic gases cases, except for dipolar gases that I won't discuss here. But let me today, at least, let me take only contact interactions. Yes.
Yeah.
Thanks. Are there other questions?
So just to clarify, are you saying that we're working in a regime where like Ty is much less than the temperature, but the temperature is much less than Tx?
Yes.
Okay.
Because if the temperature is much larger than Tx, we are not really dealing with a quantum system anymore. We are dealing with practically a classical system. So if you want a quantum system, you need the temperature to be small compared to the characteristic Fermi energy for fermions or the chemical potential for bosons. Now for fermions in cold atomic gases, this is touch and go. Jan can give me an updated number, but to the best of my knowledge, the best group can reach TF over 20 for temperatures. So this is not that low actually, if you think about it. Just to give you a number, in condensed matter, TF is 12,000 Kelvin, roughly. It's 1 electron volt. And experiments are done at, let's say, a few Kelvin. So there are 4 orders of magnitude between TF and the experimental temperature. In cold atomic gases, TF is, of course, 100 nanokelvin, which is much colder, but actually the actual temperature is only TF over 10 or TF over 20, which makes it sometimes very difficult to observe some quantum effects because simply the temperature is not that cold. In condensed matter scale, this would correspond to 1000 Kelvin. So you melt the lab, you melt the sample, you melt the experimentalist. So this is actually one problem. The problem is less acute for bosons, but is also there. And that's an important thing to keep in mind. If you want to see quantum effects, you need your temperature, or rather your entropy, to be reasonably low. Otherwise, you start having problems. Or you need to use this as a strength, as Emmanuel was doing in the previous experiment. But if you want to do equilibrium physics, you need to keep your temperature in check. And that's actually a huge challenge. I think Vasem mentioned this during his talks. It's a huge challenge if you want to observe some of the quantum effects. Are there other questions? Okay, if there are not other questions, how do we describe the 1D systems? So let me erase all this. And it's pretty clear that my schedule for the 3 lectures will have to be seriously overhauled. But as I said, it absolutely doesn't matter. I'm not running a marathon, so I will reevaluate what we will see. The important thing is that we do it well. So how do we describe? Now, if you think about it, let me take bosons for simplicity plus contact interaction. So I'll write the Hamiltonian of the system. This is something which is sum over dx. Then I have the kinetic energy, which is nab lap psi dagger, nab lap psi over 2m. That's p square over 2m. Okay. And then I will write the interaction. So the interaction is if you want density at point X times density at point X prime, but if it's a delta function, it's the square. So this is a certain coupling constant here, G, times the sum over dx of rho of X square. And this object here is psi dagger of X, psi of X. And that's what makes it extremely difficult. The kinetic energy is quadratic, so we know how to solve quadratic Hamiltonians, but the interactions make it quartic. And then you do whatever, Feynman diagrams, expansion, perturbation, mean field. See, mean field is the way to bring back this to a quadratic theory. You kind of say, oh, well, average of psi dagger psi is a number, and then I'm left with psi dagger psi. Oof, I'm back to quadratic. I would say 99% of the physics is to find the good variables to bring the theory back to quadratic. When you do Bogolyubov theory, that's exactly the same thing. So that's one route. Well, doesn't work very well in 1D. As I said, mean field theory is not super well working. So let's try to see if we can find collective coordinates. And the idea is because everything is a collective excitation, this will be the good variable. And our theory will be quadratic in this coordinate. So let me describe the method, which is due to Duncan Haldane. It has an historical name, and it was initially invented for fermions. It's called bosonization because it transforms fermionic degrees of freedom into new excitations, which are bosonic in nature. And that's why people called it bosonization. But actually, it has nothing to do with this. And in front of your eyes, we will bosonize bosons. It should be called collectivization, but I guess it carries a little flavor which is unpleasant, so we'll keep the historical name. But that's the main idea is not so much to transmute the statistics here of what we will do, but to find collective variables, collective excitations that will describe actually the physics. So in order to help you understand this, let's look at a crystal. Let's imagine that our bosons actually have crystallized so that they are forming a very nice crystal with a certain lattice spacing, which I will call A here. How would you characterize such a crystal? Well, you would say, well, actually, if the particles are not at their equilibrium position, I will introduce displacements, which will tell me actually where the particles are located. So for example, this particle has moved to the left, this particle has moved to the right, and you know this, you've done this to do the phonons in solids or whatever, and you introduce a displacement ui, which is telling you how far a particle would be from an equilibrium position. So you know equilibrium position R0I, and then you say the actual position of the particle is R0I plus ui. That's how you describe a crystal, when you get a nice crystal. Well, in 1D, there is no nice crystal, but that's what we know how to do with crystals. And then what you do an hydrodynamic theory. Okay, maybe I shouldn't call it hydrodynamic. You do a long wavelength theory. For the displacements. So you say actually UI, which technically could vary a lot. So UI could be something like this. These particles move right, the next particle move left. This particle moves right, the next particle move left. So when you move by one lattice spacing, U is very violently varying. But you say, no, that's not what happens. Actually, this becomes, this becomes a smooth function of the coordinate. And I can make a long wavelength approximation. So actually, you say all the displacements are actually very smoothly varying. This one is a little bit different than the previous one. and this one is just a little bit different than the previous one, and so on. And that's how you describe phonons, for example, in a solid. And that's nice, because then you can write a very simple Hamiltonian for this displacement, which is a quadratic Hamiltonian. The catch is that here we don't have a crystal to start with. Well, nevertheless, we'll use the same trick. So let me now give you the trick, the way it was originally introduced, but keep in mind the displacement. You will see we're doing exactly the same thing. So the trick in 1D is that you can number particles. From left to right. And you can do this because they are indistinguishable particles. So it doesn't even matter if two particles cross and you say, I don't know which was 1 and which was 2, you don't care. The one on the left is 1 and the one on the right is 2. That's it. Doesn't matter. The wave function is totally symmetric by exchange of the particles. So I just count the particle from left to right, and I know I can put a little label 1, 2, 3, 4, 5, 6, 7 on the particle. So rather than use their density, I will introduce a field, which I will call phi L of x. And I want this field to be 2 pi times an integer ni at the position of particle I. So I want this field to take exactly the value 2 pi ni, where ni is an integer, at the position of particle I. So for example, if I have a crystal, it's easy to check that actually my field is just a straight line. So phi L of x, look, 2 pi times 1, it gives me the particle here. 2 pi times 2 gives me the particle here. 2 pi times 3 gives me the particle here. So this is creating a crystal. But now, if I change my field and I make it like this, for example, I don't know, I will try to do it in real time, which might be dangerous. Now you see that my particle has moved to here. Then the other particle has moved to, I guess, here. The third particle has moved to here. And the fourth particle has moved to here. So by distorting my field, I can create any configuration I want. So if I have a crystal, the field is a straight line, and it's easy to check that the slope should be the rho zero, the average density. So I will write that phi L of x is 2 pi rho zero times x minus a field which I will call phi of x. And this field phi of x is essentially the displacement that I was talking in the case of the crystal. Now you will tell me, what is the use of this? Well, the use of this is that now I can rewrite the density, which normally is the sum over I of delta of x minus xi, where xi is an operator giving the position of particle I can rewrite it using this new field. So let me rewrite it for you. I will write it as the sum over n of delta of phi L of x minus 2 pi n. Now, is it correct what I wrote? If it's correct, it should be a mathematical identity. Actually, you see that the zero of the delta function is when xi is equal to the position, when x is equal to the position of the ith particle, phi L is equal to 2 pi n. So this is indeed the correct position for the zero. But what is wrong in what I wrote?
The dimension seems.
Dimension is wrong, you're correct. But you have to be careful when you change variable in delta functions. Actually, delta of f of x is not, if you say xi are zeros of f, so f of xi is equal to 0. Well, this is not just delta of x minus xi. There is a little prefactor which comes from the change of variable. You have to put here a prefactor which is 1 over absolute value of f prime of xi, which is the Jacobian of the transformation. If you don't do this, the integral of the delta function is not conserved. So this is a simple rule of change of variable in the change of delta function. So here I must multiply by the gradient of phi L of x and put an absolute value. Okay, let me cut a long story short, because then the rest is a little bit technicalities, and show you the formulas. So this is, I let the formulas on the slide, and just for that you can find them in a logical order in the slide. So this is what we just said. And when you use the Poisson summation formula to rewrite this, what you find is that you can completely rewrite the density under this form. I see. I hope you see my cursor. Yeah, okay. And now you could say he's completely crazy because he has rewritten the density, which was very simple, which was the sum over I of delta of x minus xi in a very complicated way. And what use can there be for something like this? So let me try to explain and of course copy the formula. So this is rho of x. So let me write it in red just to show that this is rho 0 minus 1 over pi grad phi of x times sum over p of exponential of I 2p times pi rho 0 x minus 2 phi of x. Now, this looks like a very, so pi is all integers. So the point is that this operator is an extremely unpleasant operator because it has no smooth continuous limit. The density is an operator which is extremely singular because at the position of the particle, it's infinite. It's a delta function at 0. So it's infinite, but just on the right of the particle, it's 0. So this is something which is highly discontinuous. You cannot establish a smooth expression for this kind of things. And we want to do a long wavelength approximation. So we need to re-express everything in terms of a field which is smooth, which will be our field phi here, which is the field describing the deviations from the perfect slope here. Again, this is the displacement field of a perfect crystal. Now, what we've accomplished here is to write the density in a kind of Fourier decomposition. Look, this thing here, if I take p equals 0, this oscillating factor is absent. And now I'm saying that instead of having a nice crystal, I'm having displacement like this, like that, here 0, here like this, here like this. So I'm kind of reinforcing the density in a very long wavelength way around this point. And that's a long wavelength modulation of the density. That's the Q equals 0 modulation of the density. And this is the divergence of phi here. But there is another way that I can modify the density. Let me take P equal 1 here. Then this term is essentially cosine of 2 times pi rho 0 x minus 2 phi of x, which is a sinusoidal modulation of the density. So I'm saying I have something which is perfectly periodic with maxima which are separated by a distance which is 1 over rho 0, which is the lattice spacing. And essentially, this phase here, if it was a constant, fixes the position of the maxima. So it allows me to shift right and left the position of the maxima. So I could just shift right and left, but without distorting the cosine, the position of the maxima. So this is 2 phi. So you see that if phi is ordered, the density is ordered. So if phi is ordered, density is ordered. So the field phi will be the collective variable which will tell me if my density is ordered. It also tells me that I can expect sinusoidal modulation of the density with an oscillation which is the natural lattice spacing of the system. Okay. So I have this field phi. That's one collective variable. Now, do I need another? Yes, I need another. I can write that the boson operator is the square root of the density, but then I need a phase, exponential of I theta of x. This phase is an operator. It's changing from point to point, it's fluctuating. So theta is an operator giving the phase. And you see that if this operator is ordered, then I have a superfluid. If phi is ordered, I have a crystal. So you can immediately imagine what will happen between these two operators. They don't commute. If one is ordered, the other is maximally disordered. If phase is ordered, density fluctuates like crazy. And lo and behold, this is exactly what happens. So let me continue again with the formulas. This is what I drew with the same quality on the PowerPoint than here. So, okay. And actually, these two objects have canonical commutation relation. So the gradient of phi, and that you can simply obtain by looking of the fact that psi and psi dagger have the canonical commutation relation for boson operators. So these two objects here are conjugate variables, and it means that you cannot order the phase and the density simultaneously, and this is the quantum nature of the system. Now, let me switch back to the calculation and now try to write an Hamiltonian. Now you could say we worked a lot to establish these formulas, which gives us the density in terms of this field phi. Fine, so I have this. And then another formula which tells us that the single particle operator is established in terms of this field theta, and of course the field phi, which is hidden here. Now, did I gain something? It's a dictionary. I transform psi and psi dagger into phi and theta. But did I gain something? So let me rewrite the Hamiltonian. The first part, the kinetic energy, is the integral over dx grad psi dagger grad psi over 2m. So let me be simplistic and say that I replace here rho of x by rho 0, the average density. then it's easy to see that this is rho 0 over 2m, sum over dx of grad theta square. So this is relatively simple. And now let me look at my interaction, which was G sum over dx of rho of x. And as usual, I can add a chemical potential. So let me subtract the average density square. Now, if I look at this term, you see that rho of x will start as 1 over pi grad phi times oscillating terms, except p equals 0. So this is G times sum over dx 1 over pi square grad phi square plus oscillating. Let me forget the oscillating for the moment. My Hamiltonian is now rho 0 over 2m sum over dx grad theta square plus G over pi square, times grad phi square. And we have that 1 over pi grad phi and theta, this is x prime, are simply conjugate variable minus I delta of x minus x prime. Now, did you realize what we did?
Well, now we have a quadratic Hamiltonian.
Yes. We have an harmonic oscillator Hamiltonian. So each mode, if I go to Fourier, each mode is an harmonic oscillator Hamiltonian. But this is the Hamiltonian, which initially was the Hamiltonian of interacting bosons with a contact interaction. So we fully solved the Lieb-Liniger model. Congratulations. No better ansatz, no complicated solution. By just making a change of variable and writing properly the thing in terms of the collective variable, and of course, throwing all these oscillating terms, which are there, which make the problem apparently super complicated, but you say, you are integrating over oscillating terms, so they will average to 0. I can forget them. What we just showed is that we fully solved the Lieb-Liniger. Sorry. When I say fully solved, I mean we are now in position to compute every correlation function of this model, not only at 0, but also at finite temperature, because this is just a simple, stupid, quote, harmonic oscillator problem. The technique, which is this change of variable, is what is known as bosonization. So let me show you the solution and discuss some of the physical aspects, and we'll continue, of course, tomorrow. So first, I reduce the Hamiltonian to this quadratic form. And now you see that in a way, because I have two terms, I have grad phi square, and I have pi is the conjugate pi, big pi is the conjugate momentum to phi, and this is grad theta square. So little pi times pi, big pi is grad theta. You see that if I integrate by part the canonical commutation relation here, phi as for canonically conjugate momentum, 1 over pi grad theta. So pi times the canonically conjugate momentum is grad theta. So this is grad theta square. So I have two quadratic terms. So I have two independent coefficients. which I can always rewrite as u times k and the other as u over k. So this is a pure question of reparametrizing the Hamiltonian. So this coefficient here, I can always call u times k, and this coefficient here, I can always call, sorry, this is u over k, my mistake. And the other is u times k. I let you do as an exercise that u as dimension of a velocity and k is dimensionless. Okay. This is essentially the time derivative of phi. Grad theta is the momentum conjugate to phi. So if I was writing an action, this is the time derivative of phi. So essentially, I would have 1 over u times omega square plus u times k square because of the gradient of phi times phi star k, phi k. This would be, and there is a 1 over k here, and this would be essentially the action of the system with the sum over k here and so on. So u as the dimension of a velocity, you see that omega square is u square k square. U is the sound velocity. This is describing the velocity of sound excitations that are propagating in the 1D system. And k has no dimension, but as you will see, it has a certain importance in the system. If I take the formula that I gave you, then you see that uk for the model that we look is proportional to rho 0 over 2m. And you see that you would have u over k, which should be roughly up to factors of pi and blah, blah, g, where g is the interaction. So if I want to obtain, for example, just k, I divide this by the other one. So k would be proportional to 1 over square root of g, and u would be the product. So u would be proportional to square root of g if g is small. Which is reasonable. If I have no interaction, then I shouldn't have a linear spectrum. So you see that one of the consequences is that you have a linear spectrum. Omega is u times k. I refer to you, I suggest as an exercise that you compare this to the Bogolyubov spectrum that you would get by doing a mean field theory of the interacting bosonic systems. And you will find essentially that the Bogolyubov spectrum will also give you a linear dependence, followed then at larger energy by a quadratic dispersion. And the energy is also varying as square root of the interaction for the Bogolyubov spectrum. So you could say we seem to recover the Bogolyubov spectrum, but fortunately it's not the case. And these two parameters totally control our Hamiltonian. Now to finish today's lecture, let's try to explore a little bit the consequence of these two parameters a little bit more in details. Let's forget this. Let me skip this slide. We'll come back to this. And for that, let me show you the correlations. So I have a quadratic Hamiltonian. Now I can compute any correlation I want in my problem. You just take the formulas, the expression of the density as a function of phi and theta, and you compute using the quadratic Hamiltonian. And here is the result. So this is the average, the quantum average of creating a particle at point 0. This can be done as a function of time, but let's consider for the moment that r is just position. Just for simplicity, let's forget time. I create a particle at point 0, and I destroy the particle at point R, and you find that this decay has a power law. And you see now this dimensionless parameter K is convenient because it's exactly the exponent that controls this decay. If I look at the density-density correlation, so I have a fluctuation of the density at point 0, and I look on how it's correlated with the fluctuation of the density at point R, what I will find, let's forget y is the time. So let's say it's 0. You find that there is something which decreases as 1/x². So there is a smooth variation of the density, but there is also an oscillating term, which is exactly what you would expect in a perfect crystal. In a perfect crystal, if you know that the maximum of density is here, if you move by exactly one period, you know that you have the next maximum, and then the next maximum, and then the next maximum. So if you had a perfect crystal, you should see this cosine without any decrease in amplitude. What you see is that there is a kind of perfect cosine, but the amplitude is not perfect because the crystal is distorted. So you know that you have the maximum here, next period it's okay, but then as you move forward, it's kind of distorts and loses coherence. But it loses coherence very slowly, again as a power law. And this power is again controlled by this parameter K. So what you find is a physics which is quite remarkable because it's not a superfluid. A superfluid would have told you that this function goes to a constant when R goes to infinity. That's of diagonal long range order. That's the perfect superfluid. And it doesn't go to a constant. It decays as a power law, which means you lose the phase order. That's part of the general theorem that we were discussing, that you cannot break a continuous symmetry in 1D, even at t equals 0, because of quantum fluctuations. So you cannot have a perfect superfluid, but nevertheless, you get a quasi-long range order superfluid with an exponent which is characterizing this decay and which is dependent on this parameter K. But at the same time, you get also something which would look pretty much like a convincing crystal, because it has the periodicity of density that you would expect in a perfect crystal, except the crystal is also not perfectly ordered because you cannot break the continuous symmetry, which is a translational symmetry, for the same reasons and the same theorem. So you have to lose this amplitude, and you see that you lose it again as a power law. So it has quasi-long range crystalline order and quasi-long range phase order. Sometimes people use the term super solid to describe this phase. I don't like this use for reasons that I could explain if you ask me the question. But I just want to say exactly what I said, that this has quasi-long range order in the phase and also quasi-long range order in the crystalline order. Now, everything is controlled by this parameter K here. Now, if you remember that for a very weak interaction, K is super large, it's 1/square root of the interaction, you see that you lose the phase coherence very slowly as a function of distance, and you lose the density coherence very, very fast. But now, if the interaction becomes large, you could wonder, if I take the formula seriously that I wrote, which we can discuss whether we should take it seriously, but if I say if K is 1/square root of G, when G is getting very large, let's say infinite repulsion, you could say K is going to 0. If K is going to 0, then that's exactly the opposite that happens. You see that this time you lose the phase coherence super fast, and you would lose the crystalline order super slowly, which would sound reasonably physical. So this is a strange physics where the system is quasi-long range order in two competing crystalline order type of order. You can establish a pseudo phase diagram where essentially you would say, what is the order which is lost the first? And you see that the change occurs when K is equal to 1/2. So when K is equal to 1/2, I go from a dominated, I would say, phase order to a dominated density order. So actually, you could create a kind of not phase diagram because there is no ordered phase, but dominant fluctuation, and say my system is a superfluid from K from infinity, which is the free bosons, to 1/2. And then it would look like a crystal for K smaller than 1/2. Voila. I think we will stop there for today, but I would have expected protests. No, you don't want to protest? You're too polite.
Well, someone has already
good
question at the super solid.
Yes. Okay. So super solid, let's keep it for just one more second. I was expecting protest in all the oscillating term that I've thrown away like this, you know, without thinking more and just keeping the quadratic Hamiltonian because I like quadratic Hamiltonians. You could have complained, you know, you're bullshitting us, you know. These terms are important and so on and so forth.
Do the oscillating terms become more important at higher interactions? Like, is there like...
Yeah. So maybe they become more important at large interactions, but how large is large? So one question you could ask, and we will address tomorrow actually, is how much of what I'm saying correct? Because I've thrown away a lot of terms. And yes, I justify they're oscillating and therefore they cancel in the integral, but you could have said maybe it's a little bit fast. And actually, the remarkable thing, which was found by Duncan Haldane, is that, and that was the slide that was before that I passed, is that everything I told you is rigorously exact, provided that you view this quadratic Hamiltonian as the kind of fixed point in a renormalization group sense. So all these terms that I've thrown away are irrelevant. They are not modifying the physics, and the only effect they have is to modify the numbers U and K. So actually, the expression that I gave you for U and K are wrong. They are perturbative. They are only valid when the interaction is super small. But the whole structure, the whole physics, the whole calculation of the correlation is rigorously exact, and will give you a fantastic way to analyze the physics of this system, provided I can use the precise value of U and K that correspond to my microscopic model. So one thing which is far from obvious, but you have to trust me at least for today on this, is that if my repulsion is contact and becomes infinite, then K becomes 1, not 0, but 1. So actually, this point here is the so-called Tonks limit, which corresponds to hardcore bosons with an infinite contact repulsion. But I can analyze it, nevertheless, exactly the same way by using exactly the theory that I told you. So this allowed to unravel a universal set of properties which go by the name of Tomonaga-Luttinger liquid properties, and which we will analyze much more in detail tomorrow. I will of course stop here. And this covers bosons, fermions, and spins, and cover thus most of the equilibrium properties of 1D system. Okay, we stop here, and now let me try to answer the questions. There was one on super solid, so I don't know what was the question.
Someone took your bait.
Okay.
Why don't you like the term?
Okay, I don't like to call this a super solid because for me to deserve the name super solid, you need at least one of these orders to be perfect, not quasi-long range order. So I would call a super solid something that has, for example, perfect superfluidity. So psi of R, psi dagger of 0 tends to a constant when R goes to infinity, and then perhaps only quasi-long range order in the density. But having quasi-long range order in both is too easy. If you go by that, every Tomonaga-Luttinger liquid is a super solid. But getting one of the order to be good and the other to be quasi long range order is much more difficult, much more difficult. And that's what I think should be rightfully called a supersolid. So are there other questions?
Sorry, I have a question. So you were saying that one can think of the Lottinger liquid solution as the fixed point solution. This might be a little bit technical, but let's say I'm thinking about this psi r psi dagger 0 correlation function that you've written. So does this mean that I need to actually look at it beyond some distance in order to see this behavior that you're seeing here?
Yes,
so,
you're absolutely correct. So again, let me emphasize, this is a field theory. And actually one thing which I didn't mention is that these results that I showed rest on the existence of an ultraviolet cutoff, which here is pudically called alpha. And beyond this cutoff, the field theory has no meaning. The linear spectrum theory is ultraviolet divergent if you don't regularize it. So indeed, as you said, these results are essentially asymptotically valid. Whether this cutoff is 1 or 2 lattice spacing or interparticle distances, or whether it's 1,000, at that stage, we don't know. But I will show you tomorrow, actually, it's super efficient as soon as you pass 2 lattice spacing. So yes, you're totally correct. These are asymptotic relations, which in principle requires R to be large enough. And how enough is unclear if you just have the field theory. And that's where numerics and connection between either numerics and field theory or Bethe-Ansatz and field theory will come seriously into play. Are there other questions?
I just wanted to make a commentary.
Yes.
I mean, this is a little bit of a quibble and, goes in the face of sort of historic name and all that of like real giants in the field. But I think it's more appropriate to call things that are quasi-long, what are called quasi-long-range ordered as quasi-long-range disordered.
Fair enough.
It's, the correlation function goes to 0. So that its most vivid feature is that it has no order. So
I like it, Leo. Yeah. I like it.
It's just my pet peeve that
I like it. Yes. It's quasi something, but yes.
Well, I agree. It's
at the end, it's disordered. I absolutely agree. I absolutely agree. Yes. Other questions or comments? There is something in the chat, but I don't know whether it just another question. Yes, no, so this was maybe, the super.
Yeah, maybe I have a naive question. So basically, you assume that there are a computation between the ordered density and ordered phases. That's why you put a phase, so-called the superfluid phase in the. Let's say it can be an ansatz, right? You put the superfluid phase in the formula. But so what if you have, let's say, I think maybe to me it look like you already assume there's 2 competing phases. But what if you have disorder potentials? In this case, is this still a generic solution for this?
Okay, so maybe two answers to this. So first, no, here nothing was assumed. We took the Hamiltonian. Okay, granted, we did some approximations on the solution, but we took the Hamiltonians, then we routed in terms of these collective variables phi and theta. Then we have an harmonic oscillator Hamiltonian, which we can solve fully, and we computed the correlations. So here we didn't assume, we computed, and this is what comes out of the calculation, that there is these 2 phases with the quasi long-range disorder or quasi long-range order that exists. So this is a consequence of the calculation, not an assumption. Now, to maybe go with the question you had in mind, indeed, this is a state which is very fragile. which we usually associate in higher dimension to the existence of a critical point. This is something which we usually get at the phase transition when we're exactly at TC. And here it exists everywhere. And we'll see that this is a kind of consequence or related to Berezinski-Kostelis-Thouless physics. And we'll discuss this tomorrow. But it also tells you that this state is incredibly fragile. So if you add something that helps one of these two sides, like, for example, a periodic lattice, then the crystal will be super happy and hold order very much. And that's why, for example, you will be able to get a Mott insulator in 1D with an infinitesimal periodic potential, which is added on the top of the system, regardless of the strength of this potential. So we'll discuss this tomorrow. These states, which are near ordering, are extremely susceptible to perturbation. If you were approaching a Bose-Einstein condensate that would help the phase to be really constant, then sure, the system will order very, very rapidly. And same thing for the period. So this will explain a certain number of properties that 1D systems have, like sensitivity to disorder, sensitivity to external lattices, which we will discuss tomorrow.
Okay, thanks a lot.
You're welcome.
Okay, so it looks like there is just about an hour and 5 minutes left for everyone to break for lunch. So unless there are sort of pressing, life-threatening questions to ask right now, which do come up occasionally in discussions of 1D physics, have we asked those life-threatening ones now? Otherwise, ask Thierry tomorrow.
Okay, bon appétit.
Thank you, Thierry.
Okay.
See you.